my talk is about instrumenting and introspection of the guest code in QEMU. So our team started these projects when we had software analysis tasks from our customer. We made deterministic and reverse debugging features for QEMU. I'll have a slide about it later. And now we are working on improving debugging and introspection capabilities in QEMU. So if you're working on creating new platforms or debugging kernels or software inside the QEMU, you may be interested in these approaches. The simplest thing everybody, I guess everybody tried, is just logging the translation blocks that are executed in the guest. Sometimes this helps, but the logs for the executions are usually very big, and you cannot find which processes are executed inside which memory cells are accessed, and so on. Another side, that was a previous slide about fully dynamic approach. Another side, another thing is fully static approach. It about getting the dumps of virtual memory, of virtual machines memory, and passing it to some utilities, for example, Volatility framework, which has a bunch of plugins for analysis. It can extract information about processes, files, memory regions, loaded modules, open operating system handles, and so on. But this approach is static, so you cannot look through the whole process of execution. It will be very heavy to create many dumps. You also can use GDB. There is an interface for remote debugging at the QEMU, but it has several drawbacks. For example, you can load the binary into GDB to match with the executed code, but you should guess the address where this binary is located. You also cannot figure out which code relates to which project process. QEMU cannot send the asynchronous events like control register change or interrupt to the GDB. Single stepping in the debugger may affect the timing parameters of the execution, may break the network connections. This is partly solved with the deterministic execution, which is based on account feature. This feature is almost in QEMU. For some time, for some moment of time, it is worked, but now it is kind of broken. But I hope we will fix it soon. Another drawback of GDB protocol is that it's exchanged with QEMU with kind of complex packets through the socket or something like that. So to use using conditional breakpoints becomes very slow, leads to very slow execution, because every time GDB has to check the breakpoint conditions, it has to stop the QEMU, get all registers, get the memory memory cells that are required to calculate the condition, and then continue the execution. I tried this feature in some inner loops, and it seems more like infinite waiting for successful breakpointing, not looks just convenient debugging.
I believe it is possible to get GDB to send you the expression to the stub and evaluate it on the stub, which would make it a bit faster.
Yes, we thought about it, and this is how the following approach presented on the following slide may be used. So another thing, it is interactive debugger 2, is WinDbg. It gains some more information from the virtual machine when you're using Windows. We created a stub similar to GDB stub. It is named WinDbg stub. We posted recently. We posted second version to the QEMU devel mailing list. So if you want to try it, you are welcome. So in the case of WinDbg, the communication with the QEMU is similar to GDB. It also happens with packets. That's why for our high intensive and high frequency events like instruction or memory accesses, this approach is inapplicable, and that's why we looked at the native API, like exported functions that can be used for instrumenting TCG, that will be called for memory accesses, MSR or control register changes, and something like that. And this interface will be much faster than any packet-based protocol. And we tried this for our introspection tools, for building the introspection tools, and slowdown for API tracing was about 10 to 12%. It's not very big. So there are many frameworks that use this approach. I will tell slightly about the 4 of them. The first one is PyRebox, which is not very old. It includes API for accesses to accessing the virtual machine state and to make the callbacks. And that it uses Volatility for extracting the information from the virtual machine. Another alive project is PANDA. It is similar to, it has similar API, and it also includes its own record replay implementation but just for CPU and memory, and it features taint analysis. The next one is DECAF. It is based on old QEMU version. I think it means that it was created long time ago, but I think it is still alive and used for some people. And it also has a taint analysis feature for the whole system. Another implementation doesn't have the drawbacks of the all previous. This is fatal rollback. Sounds like not invented here. It is our approach. It is similar to, its API is similar to all previous, but it targeted to our analysis tasks, and it's all the things are built upon this API are different. So looking at all of this, we found that the main requirements for such an API may be the following. This API must pass translation events, memory operation, execution exception events to the external or internal module, which can react on them and insert some instrumentation code into the executed host code. Instrumentation is straightforward. We just react on the specific operation codes or specific addresses. Maybe we filter that with for the specific processes by comparing the page page table address. And while this instruction is translated, we may accompany it with some callbacks that look like helpers in the target part of translator. This is a simple example of system call in old Linux kernels. The system call is performed by interrupt AT. We intercept this opcode and insert our callback into the translation block before making the interrupt. That's how we can trace all system calls. And therefore, we will need, in translation callback, we will need the CPU. Of course, we will need the PC because to know which instruction to test. And the translation context to insert, to call back to it instrumentation functions like variable allocation and code generation. Some frameworks tried to instrument TCG representation, but it looks simple, but it is tricky because of helper functions that are unknown, because the semantics is unknown to the instrumenting tool. In addition to instrumenting the instructions, we also instrument memory accesses. We inserted the callbacks into the helpers that perform the slow path of memory accesses, and we embed the callbacks into the translation blocks into the fast path of the memory access. Of course, this login may be used without any complex analysis, for example, for passing into the cache simulator. And we also used it for logging. This is the full log, including the in-asm and exec and our memory logging function. Sometimes this helps in simple debugging tasks. However, the generating the code, inserting the helpers may cause some problems because the buffer for generated code is limited. Generation stops on that line, max size line, when the instruction, translated instruction passes this boundary. However, we can, however, nobody knows how big is the maximum instruction will be. If we'll insert many callbacks, we can also overflow this tail. There is an optimistic comment in the QEMU code which describes this situation. We didn't figure out the solution, we just inserted the assert into the code generator. Of course, we also track the interrupts and exception. For example, for detecting the page mapping, this happens, for example, when a dynamic library is loaded, and when we detect, we implemented API tracer, which detects loading the libraries, parses their structure, and finds the addresses of the functions. There's a couple of applications of not only our approach, but also these approaches based on native API. So we have, at this moment, many implementations of such instrumenting frameworks. So why don't we should add such an API into the main line? It could be very simple, a couple of dozens of functions and callbacks, and the QEMU will be able to load and interact with the dynamic plugins or models, or maybe static models. And this will make the dynamic translator much more popular for the solving this analysis and debugging tasks. Thank you. I'm ready to answer the questions.
You have been speaking about reverse debugging and
yes.
things like that. Have you considered also comparison with Kira? You know, Kira, it also uses QEMU to record and show in a graphical and nice way.
I briefly looked at Kira, but I don't remember its key idea.
Right.
So I can't answer now.
Oh, thank you.
Hello. Yep. So yeah, I think we definitely do want an instrumentation API in mainline. I think that's kind of, if you look at, well, why do people use QEMU? I think that one of the reasons why you'd want to use it rather than using hardware is because you can, in theory, get better idea and visibility of what your guest is doing, so instrumentation is great. I think the difficulty here is that as soon as we add an API, it's really an ABI, and we need stability, and we want something that we can guarantee is going to continue to work, and that works across all of our CPUs and so on and so forth. And that's the hard bit, right? It's taking something from a research project into a production engineering context, and that's always hard, right? But mostly I think that, yeah, this is a great idea. The thing I have a real issue with is having an API that says we're going to allow your plugin to generate TCG code, and in general the idea of having a callback that happens at translate time rather than execute time. Because I think that comes down to the, if all your callback events are for things which in the guest are architecturally events, like I loaded something, I executed an instruction, those are going to stay the same across newer versions of QEMU because they're a property of the guest architecture. Think callback hooks like we just translated a new basic block, and certainly opportunities for the plugin to say generate TCG code, that can change as we change the implementation internals of QEMU, and that I would prefer not to see. Certainly in a version 1 API, right?
So
I'm sorry, that wasn't a question.
What's the performance? What is the
Sorry,
performance degradation? I was wondering, as you mentioned, that the packet protocol of GDB is pretty slow. If we were considering using the conditional breakpoints, where the conditions are implemented on the stub side and not on the GDB front-end side. This is missing right now, so there's a protocol for this, but no one implemented, of course, the stub side yet.
No, maybe protocol supports this, but QEMU does not take the conditions.
Right. Yeah, this would have been implemented, and it's also. But this is a kind of standard interface already. But of course, there are other deficits regarding GDB and x86. But for the other architectures, there is something as well. Then.
I think that would be a great bug fix, but it's kind of orthogonal to some of this stuff. Feature enhancement.
I just wondered, what is the degradation in performance of instrumented QEMU?
Simple instrumentation makes a couple of % degradation. Some of login like API login makes slowdown about 10%, 10 to 20, something like that. Thank you.